if an object is moving to the right side, momentum would be positive. It's moving upward, momentum will be positive. It's moving to the left side or downwards, momentum will be negative. What is the formula of momentum? We use the formula of momentum. We represent the momentum by small p, and that equals to mass times velocity, not speed, instead velocity, which means momentum could be positive, could be negative. Then the change in momentum is the final mass times the final velocity minus the initial mass times the initial velocity. And if in this expression mass remains constant, if m is constant, the same formula can also be written as delta p equals to m times v minus u, and we use it, ladies and gentlemen, I'm repeating again, the final and initial velocity will be decided with the sign convention, which means if a rebound occurs, the direction of the velocity is reversed, so you need to put up the sign, the opposite sign with respect to the previous one. So let's say a tennis ball strikes the wall, so the initial speed is, let's just assume the initial velocity is 3.0 meter per second. Then it says in the question, it says after the rebound it moves with the speed of 2.5 meter per second. It moves with the speed of 2.5 meter per second. But what does that mean? If the speed is 2.5, the velocity should be minus 2.5, because the velocity need to contain direction also. For the rebound, sign is reversed. And also another very important thing, if a rebound occurs, delta p is negative, because in many of the questions they would give you the value of delta p, they would give you the value of mass, they'll give you the value of initial speed, you need to find the final velocity, let's say. So whatever the given value of momentum is, that should be used with the negative sign. Mass changes and speed remains constant. So you can use the formula this way: delta p equals to delta m times v, because speed is constant, so it's not v minus u, and then it can be used as final mass minus the initial mass times the speed, if mass is constant and speed is being changed. We use it this way. Then we have a thing which is known as law of conservation of momentum. In simple words, for an isolated system, the total momentum before collision is equal to the total momentum after the collision. This is how we define the law of conservation of momentum. The general expression which we usually write is this one, but it's just a simplified expression. I mean, we can have, let's say, three masses initially. We may not have two masses, we might be having a single segment, and the collision is kind of an explosion. What does that mean? It means, let's say, after the collision, the velocity of the first object is now reversed. So this one, v1 should be negative. If the velocity of the second object after the collision is reversed, the velocity v2 would be negative. So this expression, keep it in your mind, ladies and gentlemen, m1 u1, this expression you need to improvise in all the questions. The mass of this one is m1, the initial velocity is u1. This mass is m2, the initial velocity which is 0 mu2. Now what is the improvised expression? m1, the improvised expression would be, for law of conservation of momentum, m1 u1 plus 0. What do you guys say? Plus 0. Make sense or no? Because the momentum of the second object is 0, it is not even moving. Something which is not moving has no momentum. So we can simply ignore this thing. So m1 u1 plus 0 equals to m1 plus m2, the combined mass, times the combined velocity, because they are moving collectively and both of them have a single velocity which is v. So this expression can now also be written as, and it is usually used to find the value of final velocity. So for the final velocity, it can be rearranged as v equals to m1 u1 divided by m1 plus m2. What do you guys say to this? So like I said, the collision could be elastic, or the collision could be inelastic. How do we define elastic? It can be defined by these two pointers. There are two ways we can check if the collision is elastic or not. Yeah, there was another one. Kinetic energy before collision before the collision equals the kinetic energy of all the objects after the collision. So what does that mean? It means we'll find the kinetic energy of the two bodies before the collision. We'll simply add them, and then we'll find the kinetic energy of two bodies after the collision, and collision is less than the kinetic energy before the collision. It's never greater, by the way. So you see, this kinetic energy is now after. This one is less than it is inelastic collision. Now what is relative speed of approach and relative speed of separation? The first one is moving to the right side with a speed of 3 meter per second. The second object is moving with a speed of 1 meter per second. Can the first object approach the second one? Can the first object chase the second object? In this case, yes, because the second object is moving faster. So the the first object can definitely chase the second one. So the relative speed of approach and if in the opposite direction, I don't need to draw it, we don't have enough time. If they're in the opposite direction, add the relative speeds. So let's say if this 1 meter was instead moving to the left side, now they are moving in the opposite direction. What should have been the relative speed? 4. And same is the case for relative speed of separation. Add for opposite direction. Okay, so I don't need to draw that one. Now if the objects are being separated, what does that mean? Let's say this is the first object which is moving to the right side with a velocity with a speed 2 meter per second. The second one is moving with a speed 3 meter per second. Then the first one, the object A, can never chase the object B. Rather, these objects are being receding away from each other. They are receding or they are moving away from each other. Now, what is the relative speed of separation in this case? Equals to 3 minus 2, which is 1 meter per second. So the rule is same. All we need to do is we resolve the momentum along x-axis and along y-axis. And we apply the law of conservation of momentum along both axes. So we apply the law of conservation of momentum, first along x-axis and then along y-axis. And how do we break it down into x and y-axis? We resolve the velocities into component. Just a quick example. We have two objects. A very quick example. Please focus over here. We have two objects. The second one was, let's assume, at rest. This one was mass m2. The first one is mass m1. It was moving initially with a speed of, let's say, 5 meter per second. Okay, it could be an electron, could be a proton, could be a normal mass, could be anything. It was moving forward. After the collision, the two objects, one of the object is moving in this direction. Let's say m1 is moving in this direction and m2 is moving in this direction. So this is the velocity of m1, v1. This is the velocity of m2, which is v2. And you could be provided with the angles also with the horizontal. So for example, the angle of this one with the horizontal is 30. The angle of the second one with the horizontal is, let's just assume, this is just assumed value 10. What do? You resolve the velocities into components. So if I resolve the velocities into components, one of the component of v1 would be to the top, one would be to the right. Why? Because the component was, the vector was in the top right corner. So one component to the top, one to the right. This one would be v1 cos 30. This one would be v1 sin 30. Now this one is also resolved into components, one to the bottom, one to the right, because the direction of the vector was bottom right corner. This one would be v2 sin 10. This one would be v2 cos 10. What do you do now? Let us apply the law of conservation of momentum along x-axis first. So law of conservation of momentum along x-axis. So m1 u1 plus the this is u1, by the way. The momentum of the second is 0. I don't even need to write 0, but I'm just writing it anyway. Plus the momentum of the first mass after the collision along x-axis. That would be m1 v1 cos 30. So m1 v1 cos 30, because the velocity along x-axis is cos 30, plus the second mass, and the velocity of that one is v2 cos 10. But the second, so m1 u1 plus the momentum of the second one was 0. After collision, m1 was moving to the right side. The second mass also has the x component to the right side, so both of them are positive. When we resolve along y-axis, the momentum of both of them before the collision is 0, because one of them is not even moving, this one is not moving, and the second one is also not moving along y-axis at all. It is only moving along x-axis. Now what do we have after the collision? The momentum of m1 after the collision along y-axis is m1 v1 sine 30, m1 v1 sine 30 plus the second one m2, which is now downwards. It should be m2 times v2 sine 10 with the negative sign. So you can get rid of this positive. You can write a negative sign here. And the expression, since the momentum is downward, would be m2 v2 sine 10.